Você tem ideia do quanto que o campo magnético da Terra afeta a sua vida? Quanto que você acha que você depende dele? O campo magnético da Terra, talvez a primeira coisa que você imagina é que ele é muito útil para a navegação. Você precisa dele para saber onde está o norte, com uma bússola, por exemplo. E essa é de fato uma utilidade muito grande dele, mas ele serve para muitas outras coisas que são até bem mais importantes do que isso. Por exemplo, eles protegem a Terra da radiação eletromagnética do Sol. Então eles ajudam a repelir boa parte dessa radiação que chegaria na gente se não fosse pelo campo magnético. E isso ajuda a proteger a atmosfera do nosso planeta também, porque esse vento solar ele teria a capacidade de ir removendo vários gases da nossa atmosfera, diminuindo essa camada da atmosfera, caso o campo magnético não existisse. E o campo magnético ele se forma pela interação do núcleo interno com o núcleo externo do nosso planeta. O núcleo interno ele é sólido, o núcleo externo é líquido, os dois são compostos de ferro e níquel, e como tem uma pequena diferença na velocidade de rotação do núcleo interno para o resto da Terra, isso gera uma corrente elétrica que gera um campo magnético. Geralmente a gente vê representado como um imã dentro da Terra, mas na verdade parece mais uma bola de lã todo emaranhado. E esse campo magnético não é constante, ele muda com o tempo. E o que eu vou mostrar para vocês hoje é justamente como que a gente consegue fazer para medir essas variações do campo magnético ao longo do tempo. E como que a gente pode usar essas variações em estudos paleoclimáticos, como que a gente pode usar, por exemplo, essas propriedades magnéticas do passado para entender como as correntes funcionavam e assim também entender como o clima mudou no nosso planeta. Então a gente está aqui no LSCE, eu vou mostrar para vocês um laboratório de paleomagnetismo. O que é esse? Paleo é antigo, magnetismo do passado, um laboratório que se dedica a estudar como que o campo magnético da Terra mudou com o tempo. Então vem comigo que a gente vai fazer essa visita muito legal hoje.
Welcome to the Paleomagnetic Lab at the Laboratoire des Sciences du Climat et de l'Environnement, Climate and Environmental Lab. I am Katherine Kissel, and I was leading this group for many years. We have an experimental lab which is very well equipped, and we will give you a visit of it. So the natural magnetism, what I call natural magnetism, is what exists in the archives and the geological archives. We work on paleoscience because the sediment and the rocks from the future are not well formed. So we work on archives, and magnetism is there as soon as there is some iron in the rocks, whatever it is. So the origin of the magnetism is very often coming from the lava flows, which do not have any magnetization when they are very hot. The magma is liquid, but as soon as they cool down, they get a magnetization, which is called a remnant magnetization, because it fixes the intensity and the orientation of the Earth's magnetic field upon that cooling. And so these small particles, so we can study the lavas for that. The small particles are then eroded, transported, and by the different hydrographic systems. And as soon as the system is calm enough for deposition, these small particles deposit in the sediments, whatever it is, in lakes, in river bed when it's very calm, and at sea. And these formations, then, lavas, sediments, we can study them for many different purposes. What we do here is on two main themes, scientific themes, is the story of the Earth's magnetic field, trying to characterize all the parameters we can have from the paleo field. So the rate of change, the amplitude of change, the morphology of the field during its period of stabilities, but also instabilities. And the second theme is paleo environment, paleoclimate, looking at the magnetic particles in sediments. Here we work mainly with oceanographic sediments, and so we organize cruises to look for them, good sequence for us and for our purpose. The study of the magnetism, natural magnetism in the lab is quite complex because it's like a police inquiry. We have something and we look at we have the victim and we look for the elements which made that nature. So we work on bulk and we try to decipher what is the sediment made of in terms of magnetic particles and what the lava has registered. Lavas and archaeomagnetic products. I will explain that in a minute. So it's quite complex, but we have all the equipment here to do it, and we complete it by other in our team by other measurements such as granulometry of the sediment and major and trace element analysis. This is to characterize the source of the sediment and how it is transported by the bottom current at sea, which is one of the major components of climate. So what we do is, for the Earth magnetic field, as I said, we work on many different archives. We can work on lavas, on archaeomagnetic products. Their magnetization is acquired by the same processes, which is a cooling. Archaeomagnetic products, because if you work with furnaces or potteries, what you measure is what they acquired during their last cooling. Okay? So a furnace, you can find it in place, so you have the orientation. So in that case, you have the intensity and orientation of the Earth magnetic field. Pottery, of course, it's in a fragment, so you get the intensity, but you cannot reconstruct the direction. But at least you have one parameter of the Earth magnetic field. Why do we study the Earth magnetic field? It's because it's the story of our planet, first of all. And depending at which speed it changes in the past, it can be used also for dating. Because if we have a very good reference curve of this variation, well dated, and we find it elsewhere, we can correlate and transfer an age model. The point is that the Earth magnetic field is generated in the core of the Earth, independently from the external envelopes. So it's independent from climate. And if we look at things on long enough time scales, we have what we call the dipolar field, which is the same at any point around the globe. Fortunately enough, we're not measuring it at the core mantle boundary because this is very complex. We are far from it, so it's simpler. And we reconstruct it also from sediments because these particles, they deposit at sea, and the process is done the same. It's just that they behave, I would say, like small compasses when they fall into the water column. So when they arrive at the interface, they orient themselves statistically to have their magnetization oriented parallel to the field. So it's a statistical alignment. It is good when the field is strong, and it is less good when the field is weak. So we can play with the sediment as well. The advantage of the sediment, it's a continuous process, but we only have relative intensity due to the concentration problem. And with lava and archaeomagnetic products, we have the absolute intensity, but it's discontinuous. You don't have a volcano making his lava flow every day. And the dating is also different, so we play. They are very complementary archives. The second topic for paleoenvironment is here mainly marine cores. These particles which register the Earth magnetic field, they are accompanied by other magnetic particles which do not have any magnetization. But we can excite them in the lab and see their presence. And their signal depends on their nature and on their grain size. So what we try to understand in terms of paleo environment in a core is the nature of the magnetic particles, which can give us information about the source, the size of the magnetic particles and their concentration, so which can give us an idea about the intensity of the transport, so of the bottom current. And we have also a technique which allows us to see the preferential alignment of the big particles in the sediment, giving us information about the orientation of the bottom current and eventually its intensity. So the variation of all of this during the past. So the way we proceed is in the field, we have two kinds of field. On water, at sea, with oceanographic boats, and on land for archaeomagnetic products or lava samples. So here you have an illustration of how we do in the field. Here it's in France, in the Massif Central in France. You have the mountain here, which is a volcano, the Puy de Dôme, and we sampled with a small drill with water, so that the water takes the dust out and cools down the drill bit. So you see a better view here. And then we have an instrument which allows us to orient perfectly, geographically, the core we are taking. So we measured the direction toward which we drilled and the inclination of the core with respect to the horizontal plane. At the end, we have this type of cores on which we have the line, which is a reference line, the arrows showing the bottom of the core. The top is here, the bottom is here. And you see that we have great success with the local faunas, lizard, which comes to drink, and donkeys who were very surprised. And here you have the Lachamp. Lachamp is a village in the Massif Central, very important because it gave its name to the last geomagnetic excursion, which is we were normal polarity, and it changed completely to the opposite and came back. We are the lab who studied most the Lachamp event. We were not the first one, but we were the one which studied it from sediments.
Okay.
It's a challenge to get it because you start with a state, change, and you go back to the same state. So if you don't have the right sedimentation rate or the right extrusion rate in lavas to get it, you can skip it.
How long does the event last?
So we could date it because it's quite complex, but we could give our sedimentary sequence the age model of the ice cores from Greenland with different steps. And so the ice cores from Greenland are dated annually. So we know exactly the dates, and we know the duration, because even if they missed one layer, the duration of which is well known. And so it's about, if you look at the because it's a change in direction and enormous decrease in intensity. The decrease in intensity is about 1,500 years, and the change in direction is about 600 years. So this is the only one for which we can really calculate the duration, because the dating is quite complicated in sediment at that scale.
Okay.
So the Lachamp is known for that. So we worked in many different places. Here you have a map on which all the stars here are the volcanic region in which we worked. The other part of the poster is the different cruises. Some of the different cruises we organize in the team. Here is the one off Brazil, which happened in June 23 with Aline and Vinícius, and among others. And the cores are now studied in the lab. So the marine course is taken with the Marion Dufresne, which is a French vessel, the only one making at once very long course, large diameter, 10 centimeters diameter, so we have plenty of material to work with. And we have here invented the U-channel technique, which is U because it's a U shape. And we, with edges which are thin here, so we can put it in the sediment. It is shown here in half a core. We push it into the sediment, and we have a fishing line passing below. We get it out and we close it. And this prevents it from drying and from any physical shocks. We invented that technique because we are also at the origin of the magnetometers which can study them in an automatic way. And this is, I would say, the first scan we do of the cores. And then we decide in which area we should, which area we should study in more details, which part should be studied for mineralogical point of view and so on, because we cannot do everything on U-channels. So here you have an empty U-channels, as the one I've showed, of a U-channel full of sediment. And this is the cruise from 23, Marion Dufresne, which is the name of the vessel, 23, June 2023. The core 3673 made by the Marion Dufresne. 3 is the number of the section, and there were 2 rows, so there is a row A and B. So each one is 1.5 meters long, because we are the number 3. No, it's not the well. The first one was 50 centimeters, so we are not exactly on what we would say. If we decide that we want to study other things from the U-channel, we take cubes from the sediment and we study them as discrete samples. Here is a lava core, as I shown on the picture, from Iceland. Oops. Before it was cut, it was like this. You see here, Iceland B, section B, flow 25, and we have the number 5, core number 5 in the flow. And then we cut them into samples that we also study as discrete samples.
Okay.
With lava flows, it's always a statistical thing. So in one lava flow, we take 15, 17 cores at different places, and we make the statistics. Because sometimes we don't see that blocks have moved or things like this. Okay. Sometimes the outcrops are a bit complicated. And these are bricks for archaeomagnetism. So you see that they are red because they have been cooled in air. And so the clays were modified. And these are studied also for the Earth magnetic field.
And generally, you use these furnaces mainly for reconstruct the paleomagnetic field, or
yes,
also for dating the furnace?
Both. It depends. If you have a very good reference curve, you can refer to this reference, well dated, you can refer to the reference curve and find the date. Okay. If you don't have the reference curve, you have to construct it. Okay. So from the sediment and completing with lavas, mainly from the Massif Central, we created the reference curve used now worldwide for the last 75,000 years. And very detailed. And with archaeomagnetic products also, of course, you don't go so far in time. So it's much more recent periods. And they are mainly dated by radiocarbon. But for some period, the radiocarbon is a plateau. So you have periods, time slice in which you are not precise. With the Earth magnetic field, you can refine the dating. If you know where you are, the archaeologists usually know about more or less the period, and you can give them a better date about it. So it's back and forth. You construct the reference curve, and then you use it for dating.
And you had to build a lot of equipment to do this type of measurements here.
To build?
Yeah.
We didn't build so much. We asked people to build them.
Okay.
because it's very high technology.
Okay.
So it's complicated to make them ourselves. But the magnetometers, which are in the shielded room, the idea came from here, to study the U channel. This came from here, and this is an American magnetometer, and the American came here, we discussed a lot and so on, and the group was created by Carlo Lage, who was a solid states physicist, and so who had all this kind of idea to develop the lab, because when I arrived in the lab there was nothing, almost nothing. And I saw all this development. I could participate, which was fantastic for a student. I learned a lot because I am geologist. I'm not a physicist. So I learned a lot. Yeah.
I'm geologist as well. So
yeah.
I see
And I also learned that there is no limit in the application of magnetism. I worked for 15 years in geodynamical studies, tectonic studies, in South America, in Peru, Ecuador, mainly in Greece, Eastern Mediterranean, in all the places where you have curvature, to see the role of rotation around vertical axis, because the rocks should have a magnetization toward the north. If it is not the case, it means that they have rotated. It's the only technique quantifying rotation around vertical axis. So I did my PhD in Greece, then in Turkey, then I went to Albania and to Yugoslavia, Italy. And then I stopped for paleoclimate, but I also work on pollution in rivers, metallic pollution in the Seine rivers here in France. I work with Chinese colleagues on magnetotactic bacteria, the ones who degrade in the sediment, but they leave us their magnetite.
Okay.
And so they contribute to the main signal. And things like this, there's no limit. I have a colleague working in ice cores as well with the dust, aeolian dust. Okay. There's some iron in it, so it's possible to measure. So there is no limit. And I was trained with that, opening to other fields, opening to not staying in one field. And magnetism is a fantastic tool for that, because as soon as you have iron, you have applications. So.
And it's worldwide, so
it's only that days are only 24 hours.
So can you show us the equipment?
So here we are in the room that we call the weak field room, meaning that we have several different way of treating the samples. Either we heat them to reproduce what was made in nature, or we applied fields, different fields, alternating fields, high DC fields, so we torture them without touching them. I mean, it's just the magnetization that we torture. And so this is a kind of forcing the signal to understand what is behind, what is the carrier, what is the... So we have a room for applying weak fields. Then we have a room for zero field, and in another room, the electromagnets with high fields. So we are isolated here. Here we have furnaces. That's also our idea, developed by a small company, French company. This is dedicated to the rocks which acquired their magnetization by cooling. So we reproduce them. What happens is that when they cool down, their magnetization is proportional to the paleo field. We measure this magnetization, we ignore the paleo field, and we look for it. So we reproduce the experiment in the lab with a field, a known field. So the magnetization we measure is proportional to the field we apply. The problem is to be sure that the correlation coefficient between the magnetization in the field is the same in the lab as it was in nature. So it's not only by heating the sample once, we heat it several times. We control at low temperatures that we have not oxidized the samples, because when we heat something, we oxidize it. So we have plenty of warning like this, and plenty of cautions we take during this experiment, which is quite long. We measure these samples about 2 months long, twice a day. Because we heat, we cool, we measure, we reheat, we cool, we measure, and so on.
But the first step is to measure the natural signal, and then you erase it and start to recreate several
at a progressively higher temperature. These furnaces are special. We can have neutral gas in order to avoid oxidation. And around here you have a solenoid creating a field, the field you want to apply. And so what happens is that you measure the sample, natural magnetization. You heat it at about 100 degrees, you will demagnetize it, of course. But because it will cool down with a field apply, you will superimpose a magnetization which is acquired in that field, what we call the induced magnetization. Then you repeat the measurement, but with the field reversed. Okay. So that by the half sum of the half difference of the final products, you can have the natural one remaining or the induced acquired. Okay. And so on and so on and so on. And sometimes you go back to lower temperature to be sure that you have not affected the magnetic mineralogy. It's a very exigent thing, but it works quite well. So we have several furnaces that have different capacities in terms of a number of samples and different dynamic. So the big one cools down slower than the medium one, and the very small one is for a specific experiment we want to test. So here you can notice, if you go around, that all the furniture are in wood, which is good for me. I like wood.
You like wood,
because we're not allowed to have any metal.
And of course, that's because of the field.
Even when we measured with this instrument here, we are very careful not to move the chair. Here is our third room in terms of magnetism, in which we apply the high field. So it's full of big electromagnets. So the first electromagnet we can see, for example, this one, it's more than 500 kilos, suspended, okay? It doesn't touch the floor in order to avoid the vibration. Okay. And so this is what we call the Curie balance. It's VFTB, variable field translation balance. The principle is quite simple. You put your sample, powder, in sample holder like this. So you put your sample in this one, you block it, and you put it here, horizontally here. And you move the sample holder in that direction so that your sample will enter into the magnet. And if you look at this, there's a magnet, there's a furnace in it. The yellow part here is a furnace. Okay. So we have the magnet plus the furnace. And the point is that the sample is attracted by the field in the magnet. And when we heat it, it is demagnetized, so it's less and less and less attracted. So it will go backward. So the principle is, indeed, it doesn't go backwards. There is a current which maintains it at the same place. So when the current is strong, it means that the magnetization is weak, and vice versa. So we measure here with the temperature how the magnetization decreases, and we cool it down. Either it is reversible or it is not. There is some transformation or not. At which temperature does the magnetization disappears? For example, you have characteristic temperature for magnetite is 580 degrees. Okay. Hematite is 690 degrees. Sulfides is 350. So you can discriminate. Some of them have the same characteristics in terms of field. And this is why with the U-channel we cannot solve everything. Okay. But we go to this instrument afterwards trying to discriminate between different magnetic mineralogy.
Okay, and how long one measurement takes?
You decide, the users decide at which speed you want to heat the sample. But in routine, I would say that it's about 1 hour, 1.5 hours.
Okay.
For heating and cooling.
Okay.
And then sometimes if we see some transformation, we heat again and cool again.
Okay.
And if we see a transformation and we don't know when it occurs, we can make partial heating to 100, cool, 200, cool, so on, to see at which temperature does the transformation occur. So here we play with field and temperature.
Okay.
Here it's another instrument, which is quite a recent one, a very modern one, with which we obtain hysteresis curves. I'm looking for drawing, but I can't find it. So, same principle, the sample is fixed here and goes into the polar pieces of the magnet. And everything is controlled by computers. Okay. So the computers, we ask it to apply a field, for example, to 1 Tesla, and then to -1 Tesla, and it measures the magnetization back and forth. And it is not reversible. You have an hysteresis curve, meaning that the two ways are not superimposed, and the width of your of the non-reversible part gives you also information about mineralogy. You have characteristic values, which gives you also what is inside, information about what is inside. This is the most modern one. This is the grandfather. This works very well. We acquired it in 1981. And but it takes only very small amount of sediment. So for sediment it's okay. For big rocks, lava flows, it can be biased because it's not enough. So this is a high field room.
Okay, perfect.
Not good for people who have pacemakers.
Oh, okay.
When we apply a field, 1 Tesla, and then it decreases, and when we go back, and there are characteristic points. This one here, which is a saturation, and then this is field, and this is magnetization.
Okay.
So this is a saturation magnetization, and this is what we call the coercive field here. It's totally symmetric. The curve is well symmetric, and sometimes you have narrower, meaning that you have bigger grains. Larger, you have smaller grains. Sometimes you have narrow here, and then it goes opened like this, meaning that you have 2 different magnetic minerals, and so on.
And based on the shape of this curve, you can split different minerals, so you can tell what is inside.
Yeah. And of Brazil, when we looked at the results with Aline, it's very complicated in terms of mineralogy. Okay. Because you have different sources. We are close to the continent, different sources, different type of rocks, different climates. And so you will have a beautiful climatic signal by just looking at the magnetic minerals. Okay. I can guess what is behind, but she has to check.
Perfect.